my fellow assassins, to another episode of the Dark Assassins Podcast, the show that dives deep into not just technology, but the concepts, software, and procedures behind it all, and explains it so simply that even your grandma can understand it. As always, I'm your host, the Dark Assassin. I hope you all brought your shovels and your hard hats for this episode, because we are going to be digging all the way down to the binary level of a program, to the binary level of a CPU. We're going down to the literal ones and zeros when it comes to programming, and I'm not using that as any kind of hyperbole. We are actually going to be talking about literally manipulating the individual ones and zeros in order to more optimize your programs. So you're definitely going to want to stay tuned for that conversation. But before we get to that, let's start off with our trivia question. So we've talked a fair bit on the podcast about 10 gigabit networking, in part because I've been slowly trying to get 10 gigabit networking into my home lab, and of course it's been a very, very slow process. But as part of that conversation, we've talked a lot about the connector that's used, which primarily is the SFP Plus connector. Now, this week's trivia question is, what is the name of the connector associated with 40 gig networking? So what is the connector associated with 40 gig networking? Now, as a little reminder, if you listened to the episode we did on networking, the networking technologies and kind of the infrastructure behind networking, we talked about this connector. So for some of you, this is probably going to be easy. Or I guess if for any of you that are really into the networking space in general, this is probably going to be an easy one for you. But just for the rest of you out there, we have covered this before. So I didn't say it was going to be on the test, but it's on the test now. But anyway, that is your trivia question for the week. So speaking of things that I have talked about a fair bit, how many times on this podcast have I mentioned how funny it is to see how quickly a release of a piece of software, an operating system, what have you, goes from a major release to a point release? Now, what I mean by that, for those of you who aren't necessarily so inclined to the terminology of software releases, so your major release is something like your something 0.0. Now, usually this is going to be something like a 2.0, 3.0, 4.0, something like that. Although there are some times where you'll have minor feature releases, so that'll be like your 2.1s, 2.2s, that kind of a thing. And then the point release is generally that third digit, that 2.2.1 or 2.2.5, something like that is generally a point release. Although depending on the changes, it could be going from 2.0 to 2.1. It just kind of depends on what all is involved in the changes. But it is always funny to see when you have a more major update, which is one of those first two numbers. It's always funny to see how quickly that number increments again in one of the other digits. I've been a culprit of this. I, on numerous occasions, have released a version of a piece of software that I developed, only to then realize that I broke something or there was a bug in it, and then had to issue a point release within like a couple weeks of the release coming out. So I can't really say much because I am right there with you. But the reason I bring this up is because back on September 18th, which as of the time this episode goes live is about 2 weeks ago, Apple released their iOS 17.0 software update. So the big release, we talked about some of the new features from WWDC a couple months ago, and they finally got to releasing that new version in in time for their new iPhone launch. And within about 4 days, I think it was, they released a point release, that being iOS 17.0.1, due to some actively exploited vulnerabilities in the wild. So that's always fun to see. And then as I talk to you, just shy of 2 weeks from the initial release of iOS 17, we're already at iOS 17.0.2. So they have issued yet another point release, again due to some security-related vulnerabilities. So it's always fun to see how quickly these point releases come out from a major release, which is why there are some out there that when a new point release comes out, a new release comes out, they'll usually give it like maybe a month or so before they actually update in order for all these kinks, as we can see, to be ironed out. But it's just something that's always fun to watch, because whenever I see a new release of some piece of software, I'm just looking at my metaphorical or fake watch on my wrist, being like, okay, when's it going to happen? When's the point release coming? Because it eventually comes, and sometimes it's a lot sooner rather than later. In this case, it was quite soon. But yeah, so if you are on iOS 17, hopefully you've been keeping up with your very frequent updates, because in some of these cases, some of these vulnerabilities that these updates patch were due to some exploits being actively exploited in the wild, so definitely want to make sure that you are up to date on those. And with that, I think that's a good segue into this week's cybersecurity tip. So for this week's cybersecurity tip, it's a pretty simple one, and that is to lock your doors. And moving on, just kidding. But I'm not actually kidding about the lock your doors thing. And some of you are probably thinking to yourself, have you lost your mind? What in the world does locking your doors have to do with cybersecurity? Now, part of cybersecurity, as we've discussed, is kind of a broad field, right? It's not just the making sure that your firewall doesn't have any open ports that it doesn't need, making sure that you don't have any software that you shouldn't have installed, making sure that you only give users permissions for things they need, that kind of a thing. That's all well and good. But we've also talked about other things that are related to cybersecurity, things like a backup strategy or a disaster recovery plan. There's a lot more to cybersecurity than just trying to prevent hackers and threat actors from breaking into your stuff and making you have a very bad day. And one way that they could theoretically make you have a very, very, very bad day is if they actually broke into your house or your data center or wherever you have your technology and messed it up that way. So physical security also plays a pretty important role in the realm of cybersecurity, because it doesn't matter if you have a firewall that makes the North Korean firewall look like, mesh and everything can just go straight on through. Because if someone can get physical access to your systems, any kind of network-related protections you have is kind of a moot point at that point. Now, obviously, you should still have some protections against that, like if they get physical access to your system. Ideally, they wouldn't be able to access because you'd have, accounts on there with password permissions or some other kind of authentication. Maybe you're just a baller at your house and you have all your systems require two-factor, whether that's a password and like a hardware key or something. But regardless, there is again the chance that they could, get to the system and maybe take out the hard drive or take out the SSD or take out the storage or what have you. Now, again, you could counter this by encrypting your drives. But depending on the state that you potentially leave your machines, they are potentially more susceptible to attacks. Like, for example, if your machine isn't in a powered off state and it's actually powered on, the fact that the drive's encrypted probably isn't going to do a whole lot, because generally speaking, the drive is really only encrypted when the machine's powered off, and then once you actually power on the machine and boot into the operating system, that's when things kind of get decrypted, so you can, actually use the system. And then there's some other things too about potentially passwords not necessarily being as tightly encrypted, or potentially a little more available if the system's powered on rather than a powered off state. But regardless, if someone actually gets physical access to your systems, they could, in the event, potentially break into your systems with physical access, but they could also just break your systems in general. And if they actually physically break your systems, there's really no recovering from that unless you buy other hardware. So you definitely don't want that to happen. And this idea of physical security also kind of plays a role into software vulnerabilities and how they're scored as far as a severity aspect. And the reason why that's important is because you theoretically could have, say, an exploit in like the system's BIOS or the firmware or something, which is like hardware level stuff. But in order to perform the exploit, you need physical access to the system. So it's not something that like you can do via a network exploit or through like a buffer overflow or any kind of, your typical exploit. You actually have to have physical access to the system. Generally speaking, while those can be pretty severe and critical vulnerabilities, it comes down to the ease of exploitation, because part of the grading system for, how likely a cyber threat is going to happen, it comes down to how easy it is to exploit. In this case, if it's like a BIOS exploit where if you mash, say, the space bar like a bunch of times, it can like bypass some checks and you can boot into whatever you want. Obviously, that's a pretty decently sized vulnerability, and it's super easy to do. But on the other hand, the access levels required for you to actually perform that exploit potentially are pretty low, because you actually have to have physical access to the system. So that is potentially why some grading systems you might see a vulnerability that looks pretty severe but isn't necessarily rated all that high, and that is the potential reason of why that is. Or you might see a vulnerability that doesn't seem to be all that severe but is rated higher because of maybe how easy it is to do and how widely accessible it is to occur. Like maybe, let's say you have a piece of software that's running some kind of network protocol, and you ensured that you can't do any kind of arbitrary code execution on it, so you at least have some kind of checking for your bounds or whatever, so you don't have any kind of like buffer overflows. But it still can crash the system with bad user input. So obviously that's something that's not good. But because it's networking based and how easily it is to perform, that might rate higher than, say, something like a BIOS level threat that someone would actually have to have physical access to the system. Now, obviously, in both cases, those things should be patched. I'm not saying that, one doesn't matter if it's patched or not. Obviously, both should be patched. But part of determining of how the severity of a vulnerability partly comes down to the ease. One, the ease of access, how easy is it to exploit the vulnerability, and two, what are all kind of the prereqs, if you will, in order for you to be able to exploit that vulnerability. Is it some Metasploit module you can just hit run and it'll do it for you? Or is it something that you have to write like 10,000 lines of code and have an intricate knowledge of every kind of networking protocol in the book and how to perform 10 different different types of lateral movement just so you can crash a program. Something like that is obviously not going to be nearly as high on the priority list as, something that I can just type in a character rather than a number into a text field and cause the program to crash or perform an undefined behavior. So going back to the physical security aspect, doesn't matter how good your cybersecurity is. If your physical security is pretty bad, you can still have a very bad time. So make sure that you are taking the precautions necessary to physically secure your systems, in addition to securing them cyberly, in having good cybersecurity, good cyber hygiene with your systems. So that is your cybersecurity tip for the week. Now, tangentially to nerdy things, potentially future nerdy things, there's some big news, kind of sort of home lab related, that being the Raspberry Pi 5 just got announced. Now, some of you might be thinking, wait a second, Raspberry Pi 5, I still haven't been able to get a Pi 4 yet, which I think at this point, if you wanted to get a Pi 4, you probably could, since they've been pretty much back in stock for, I think, the most part in the past couple months or so. But the Raspberry Pi 5 has just been announced. It's supposedly going to be available sometime in October. I don't think there's been an exact date on that yet. Although if I had to guess, I would assume probably end of October. But like I said, no definitive date has been announced. Some of the new features coming to it is there is finally a power button. So you actually have a means to power on and off the system. Now, I know at least for my Raspberry Pi, which is a 3B Plus, the kit that I had got with it did have a quote-unquote power button, but that was more or less like a kill switch adapter that you could plug in to the power jack, which was micro USB port, and then you plug the actual charger into that kind of adapter, and then it has like a button on it that you can kind of sort of make it act like a power switch, but it wasn't really one. But there's officially a legitimate power button on the new Raspberry Pi 5. Some other upgrades to the Raspberry Pi 5, it has a new CPU. It's a quad-core A76 CPU clocked at 2.4 gigahertz. But for those of you who that just sounds like a bunch of nonsense gibberish, the main takeaway here is that it's at least 2 times as fast compared to the Raspberry Pi 4, while being more power efficient. So if you thought your Raspberry Pi 4 was sucking down way too much juice, well, now you can get twice, if not more, performance for even less juice. So that is always good to see. Also, another big improvement to the new CPU on board is it also brings ARM's crypto extension for hardware-based cryptography. So basically what this means is your CPU doesn't have to manually brute force the crypto algorithms to do the various types of cryptography for like encryption and decryption, all that good stuff. It now has hardware-enabled stuff inside the system on a chip in order to be able to do that processing. And what this means is you can see increase in speeds of up to 45 times compared to the previous version. So that is pretty awesome to see. So this would probably make for a pretty banging like VPN solution, like mini VPN solution with the built-in onboard cryptography stuff. Probably be pretty good for that if you're looking to do something like that. The GPU also gets an upgrade, so now you can decode H.265, which is a pretty beefy pretty beefy video encoding. It's kind of known to bring systems to a halt if they don't have the appropriate hardware encoders and decoders for it. So you can now decode that H.265 at 4K 60, and it can also handle 2 4K monitors at 60 hertz. So for all of you out there that have battle stations, you can now hook up two 4K displays running at 60 frames per second, like a boss. It also has a PCIe connector via an FCP or a flexible printed circuit, so you can now have some PCI expansion with the new Raspberry Pi 5. You do have to kind of get like this ribbon cable adapter thing to PCIe express board thing, so it's not like, you can just plug your GPU into the side of the Raspberry Pi or anything like that, but it does have some PCI support. One thing that is, I don't know if I would necessarily call it a bummer per se, but it is a singular lane of PCIe Gen 2. So for context, we are now at PCIe Gen 5. Now, granted, Gen 5 isn't necessarily super widely available. I mean, it's starting to come out, but pretty much Gen 4 is kind of everywhere at this point. Now, I did see that you can, if you kind of hack into the settings inside the operating system, you can trick it into thinking it's Gen 3 and you can get PCIe Gen 3 speeds, but I don't believe that's officially supported, so your mileage may vary, but just so you know, it is theoretically possible anyway. And as far as pricing goes, it is currently, they're going to charge $60 for the 4 gig model and $80 for the 8 gig model. And I believe, depending on where you go, you can actually start pre-ordering these if you're so inclined. And if you want even more information on the Raspberry Pi 5, Jeff Geerling did a pretty spectacular video kind of covering a whole bunch, pretty much everything that I covered plus more. So if you're interested, you can check that out. I'll have a link in the show notes. And I'll also have a link to, I guess, the news or blog posts that Raspberry Pi put out on it as well, so you can go and read that too. Now, one thing that I did kind of notice about the new Raspberry Pis is, as far as the pricing structure goes, I have seen some people commenting online that with it being slightly more expensive than previous models, it's not necessarily something you can just like impulse buy, with it being like $60 or $80 depending on which version you get. Plus the fact that you can find like mini PCs that are cost either as much or in some cases cheaper and get a lot more performance. Now, granted, depending on the mini PC that you buy, you probably be using more power, but again, we're talking like maybe 10 watts compared to like 2 or 3 watts or something like that when talking about idles. So I mean, it's not necessarily a whole lot of power difference, plus you're getting a lot more power and you're getting x86, which has a lot more software compatibility. Although with that said, Raspberry Pi is very, very good about when it comes to their software compatibility. Now, other like ARM-based Linux systems and just ARM systems in general, the software compatibility is kind of hit or miss, but Raspberry Pi has a really good collection of supported software. So that's not necessarily as big of an issue as if you went with one of the numerous Raspberry Pi knockoff or clones or whatever you want to call them. Those generally don't have as good of software support as the Raspberry Pi does. But regardless, I think this is a pretty cool looking upgrade. Maybe I'll pick one up at some point. I guess we'll see what the availability is like come October when these things are supposed to start shipping. But yeah, I just thought I'd bring that up, since that is something that I know a lot of people that deal with home labs and kind of like to tinker around with stuff. The Raspberry Pi is kind of like a staple there, so just thought I'd bring that up. And speaking of home lab stuff, I didn't really do much specific with my home lab this week, but there is still some stuff that we should talk about in what nerdy stuff have I been up to this week. So this week I pretty much got back to programming, specifically working on my video game a little bit more. And it's been a few months, and literally all I have to show for it is like 0 new features because literally all I've been doing is trying to optimize things and fix memory leaks, and that's pretty much been the story for the past I don't know how many months now. And that trend continues because rather than actually moving forward and implementing new features, I continued to go back and rewrite things I had already written in order to better optimize them. Now, when I say that, I'm going... So, if you'll recall, I specifically created a slimmed-down version of the larger Pokemon class that I was making, and made a slimmed-down version to better optimize and more memory efficient and that kind of a thing. And I decided that how it was currently was not good enough. It was still too bloated, and I needed to optimize it even further. So this week, I managed to take it from being roughly 100 bytes worth of size for a singular object down to 76 bytes. So we cut down about a quarter of the size just by a couple minor optimizations, and those optimizations being variable placement and bit packing. And to those of you who aren't necessarily low-level software developers or all that familiar with kind of low-level programming or programming in general, those probably sound like kind of bizarre topics. And specifically, those of you who aren't necessarily low-level programmers are probably wondering, what the heck does variable placement have to do with memory optimization? And boy, oh boy, it has a lot to do with memory optimization. So that is what I wanted to get into this week as kind of the main topic of the week. And that is kind of this idea of bit packing and optimizing your memory structures for your objects. So bit packing in general is pretty common in most languages. C and C++ have it, Python has it, Rust has it, Java has it, and that's just a few. There's probably a lot more that have it as well. But basically, it can be done by manually packing multiple values into a single variable. Now, I had already done this once in my initial plan to optimize the Pokemon class, that being taking the moves, and rather than having a four different move objects in a single Pokemon, you instead have a single integer value that contains the ID of the move, the current PP, and the total PP of the move, because from that you can see how much PP you have left, and you can go directly to the move through the lookup table in order to get things like the move's type, how much damage it'll do, and all that good stuff. So I had already dabbled in this idea of bit packing, or packing multiple values into a single value. But I decided to take it a step further because there was a lot of kind of like miscellaneous data that had a bunch of like small values that quite honestly didn't deserve to be as large as they were as far as space, so I might as well do some bit packing and compact all those values into a single value in order to save space. And the other thing I also did, like I mentioned, was reorganize the variables inside the class itself to also save space. And we're going to get into an example of that here in a little bit as to how that can actually save space. But there are a couple ways that you can actually go about doing this bit packing. So the one is kind of the one that I already talked about, where you essentially take, say, a single integer, which is, is 4 bytes or 32 bits, and you just kind of divide up those 32 bits into smaller bit segments in order to store your data. So like in the course of the move example that I talked about before, the lower byte was the total PP, and then the second byte was the current PP, and then the upper 2 bytes was the move ID. And that's just one way that you can pack multiple values into a single integer value. Now, obviously, for anyone that hasn't done any kind of like bit manipulation or bit shifting or bitwise operators, the code in order to do that is quite unreadable. It is not very intuitive, and quite honestly, you kind of have to think about it in some cases. So, but the nice thing is, because of how I get in the one sense, it's pretty easy to do, because if you know what your offset is or how many bits from 0 that you want to start at. So, for example, if the first byte is one number, then you can shift up 8 bits, and that's your second number. So as long as you know where your offset is, it can be really easy to write a single function that can set any bit and any number of bits in an entire number with ease in just a single function. So all you have to do is call that function and you're good to go, which is what I ended up doing. But for new programmers especially, it can be kind of a hard concept to grasp, and actually looking at the code is, like I said, quite unreadable. So it's a really good idea if you are planning on doing any kind of like bit packing or bit manipulation in this way of packing multiple values into a single integer value, that you do a really good job of naming your variables, because that'll help you in the future try to decipher what the heck you were trying to implement. Because one thing that we've talked about on this podcast is, just because you write a piece of code that makes complete sense to you now, if you leave and come back to it in a couple weeks, couple months, even years, there is a good chance that you're going to have no idea what that code is doing. So having good documentation, good comments, and good variable names can help alleviate some of those issues. Now, but that's not the only way that you can pack bits into a single value. So you can also do this with structs as well. And the way that you can do this is basically specifying how many bits a given value is going to take up when it's created. So normally, if you create, say, a Boolean value in a struct, that's going to take up 1 byte. Now, if you're familiar with what a Boolean is, you know that is just a true or a false. Or in terms of binary, that is just a 1 or a 0. So really, there's no sense in having a Boolean value take up a full byte worth of memory when it obviously doesn't need to. So what you can do is you can express this in your struct as like, for C and C++ syntax, you can do bool b:1, and what that is basically saying is this Boolean value called b is going to take up 1 bit worth of space. Now obviously it's gonna round up, so like if you only have that 1 Boolean value, it's not really going to do you much good. But like, for example, if you wanted to pack, say, 4 or 8 Booleans into a struct, and you didn't do that, your singular struct would be 8 bytes. Whereas you could individually pack all 8 of those Boolean values into a single, one byte integer value, like a uint8 or an unsigned char, that kind of a thing. So I guess you could say the unreadable way to do it would be if you wanted to, say, handle these 8 Boolean values. The unreadable way would be to pack all of them into, an unsigned char or a uint 8 underscore t, if we're talking like C, which is basically an unsigned char, essentially is what it turns out to be, which is a single byte value, or contain a value that contains 8 bits. And what you can do is you can just, if I want to get say I don't know what you would have with eight Boolean values, but if you say you wanted to get the 5th one, you could just check bit 5, see if that's a 1 or a 0, and then return that for your value. So that way you could pack 8 Boolean values into a single byte, rather than having, in the case of a struct, 8 Boolean values taking up 8 bytes. So as you can see, one is way more efficient than the other. But if you go back to what I was talking about, you do that bool b:1 thing, that is basically doing the exact same thing. So if you had 8 of those, your struct would only be 1 byte in size. So that's one way that you can bit pack in a more human readable way, I guess we can say. Now, when it comes to organizing the data, that's also a key factor as far as size is concerned. But the act of going back to the colon thing, the setting data in a struct where you specify how many bits a individual value takes up is definitely a lot more human readable, I would say, especially for beginner programmers, than compared to doing a bunch of bitwise operations and bit modulation, right? So the struct way is definitely I would say the easier way to go about it. But the reason why I personally didn't go that route was partly because I wanted an easier way to serialize data, plus I wouldn't have to worry about any kind of equals operators for comparing a struct. So basically me being lazy, I guess you could say. But the reason why the serialization reason I went with is it's a lot easier. It's really easy to serialize a single integer because you can just call like a toString method to convert the number to a string, which, if you're trying to save it to a file, boom, you're done. And then you can just read that number back in and all your data's back, and you don't have to worry about setting values. So from a code perspective, it's probably less lines, but that comes at the cost of being a little bit less human readable. Although I would like to think that I did a good job documenting the functions that I use in order to actually set the various values and get the values out. But with that said, the other nice thing about it was because I was just packing everything into a single integer value, none of the rest of my code actually needed to change at all. And the reason for that is because if I, say, wanted to get the met location of this Pokemon, I didn't have to change the get met location value at all, right? Like if I want to call that function, I don't have to change anything from the caller's perspective because it's still going to return a met location. The only thing is, on the back end, as far as like the getter's concerned, I just have to change how I get that value. Rather than just returning the met location, I then, call my bit function to get the certain bits associated with the met location and then cast that as a met location and return that value. So from the actual caller's perspective, the person using this get value and even the set values for that matter are completely oblivious to what's going on behind the scenes, while all the while getting all the benefits of the decreased memory footprint. Now, I have also talked about, so that's a lot about like the bit packing and whatnot, and how you can cram a lot of data for different values into a single value to decrease your memory footprint. But that can only get you so far, because if you poorly optimize where your values are placed inside of your structure or your class or what have you, you will basically can sort of undo some of those optimizations by packing data into a single value. And what I mean by that is basically you need to align your structs and align your classes, because not all variable types are the same size. And I think that should probably be fairly obvious, because if you think of the maximum number that, say, a 32-bit integer can hold versus a 64-bit integer, they are vastly different, because the 64-bit integer obviously has more bits, and more bits means more bytes, which means more data, which means more memory. So obviously, the various data types have different memory requirements when it comes to them. And as a side effect of this means that depending on how you add your variables to your struct, the compiler will actually insert padding in between your variables if they don't align. And basically what this means, if, say, you have two variables next to each other inside your struct that aren't the same size, your compiler is going to add some padding in there in order to make sure they're set right as far as the object is concerned, which adds additional memory to your struct that you didn't necessarily intend to. So this causes more memory usage. Now, it should be noted that you can actually manually tell the compiler to pack the struct in order to not have any excess, to make sure everything's aligned. But it's just general good practice to do it yourself rather than relying on compiler stuff. Because, back in the day, you might not necessarily had that luxury, but also, I think we've kind of talked about before, and I'm sure anyone that's used modern software has kind of noticed that the days of developers writing super optimized software has pretty much gone by the wayside, in the sense that you have all these applications nowadays that take up so much memory, and they're just not necessarily as efficient as they were back in the day when, system hardware requirements were like serious limitations, and you really had to pull you pretty much had to optimize everything to pull every ounce of performance out of the system and stay within its limits. And that has sort of gone by the wayside and isn't really as important to some people, and in a way it kind of just makes people write more sloppy code and more memory hogging code, not necessarily because it's leaking memory, but because it's taking up more memory than it needs to. And we're going to get into an example here of that in action. But another thing when it comes to aligning your structs like this, and why it's important, is because there are certain technologies and protocols out there, specifically like networking protocols and other older standards that you may or may not have to interface with, but specifically networking, which basically we all interface with, because pretty much everything we do these days has some sort of networking interface to it. And when it comes to the networking protocols, things have to be in specific spots. And what I mean by that is, if your checksum is not where the checksum is supposed to be, you're going to be in for a bad time. So you need to make sure that all of your bits align properly to be where everything's supposed to be. And this is why bit packing and struct alignment is so important when it comes to building good programs. And this is an actual real world use case, rather than me just kind of, wishing that people would write more optimized code. But in addition to that, if you do any kind of embedded systems related coding, That's another instance where you want to make sure that your structs are aligned, and you pack your bits and into smaller values, so you're not taking up as much memory, because embedded systems, unlike your desktop computer or whatever, don't have gigabytes worth of RAM on board. So you really have to be conscious about the efficiency of your program, because they are constrained in both CPU and memory aspects. So you really have to watch how you're doing your coding. So that's kind of some reasons why this matters. Now, getting back to the alignment aspect of it. So you would think that if you have two structs with three variables, that being two integers and a long, which is kind of another version of integer. One way you can think of it in this case is the integers are 32-bit values and the long is a 64-bit value. You would think two structs that contain, two integers and a long would be the same size, right? Well, guess what? You're wrong, because they can be quite different in regards to size. So as an example, let's take this struct alignment. You have a struct that goes integer, long, integer. That struct takes up 24 bytes worth of data. Now, here you can actually see the padding that the compiler threw in there. But let's go to an optimally aligned struct to see the difference. So in this case, this struct goes integer, integer, long, and as far as the data is concerned, it contains the exact same data, right? Two integers and a single long value, just like the one before it. But this one that goes integer, integer, long only takes 16 bytes worth of data rather than 24. So here is a perfect example of how misaligning your variable types can lead to the compiler adding in padding into your structure, and therefore it taking up more memory than it actually needs to. Because if we actually look at this, we can see that a 32-bit integer takes up 4 bytes, right? And we have 2 of them, so that's 8 bytes. And a 64-bit integer takes up 8 bytes, so 8 plus 8 is 16. So the optimal alignment for our struct is 16 bytes, as we see with the second struct. But the first struct takes up 24 bytes because we went integer, long, integer. And the reason for this is because the compiler and the program can't fit a 4-byte value with an 8-byte value, because, theoretically, if we're talking about a 64-bit computer here with addresses that are 8 bytes long, you can't fit 4 bytes and 8 bytes into the same memory space there. So you have to add padding in order to then fit the extra 8 bytes. So that's where the padding comes into place, and you're essentially throwing away 4 bytes worth of memory in order to accommodate your unoptimized aligning of your struct. Now, some of you are probably thinking, oh, big whoop, that's, 16 bytes versus 24. That's nothing. And you're right, but you have to think about this at scale. Because, yeah, on the small scale, it's not much, but you only have to account for, a few structs worth of, instances of a struct, like, say an array of these structs, and you're talking magnitudes of structs more for the same number of them. So this grows pretty quickly and can kind of sort of get out of hand. And this is just a small example, right? this isn't even taking into account if you have structs that contain structs or classes that contain classes. There are a lot of real-world scenarios where you'll have, like, say, a single class that maybe contains a couple other classes along with a bunch of other different variables of its own. So if you have a lot of these unaligned classes and structures, the amount of memory that you're just leaving on the table and taking up that you don't need to can grow pretty quickly. And if we take it back to, the Pokemon example, right, that I'm trying to make, I mentioned how much memory can be saved just over the course of, say, having like a couple hundred of these little creatures, right, with the original class versus the optimized version of class, and just how much data that is. Now imagine if all that, being not aligned properly. I even mentioned, 24 bytes, I think, was what I saved by better aligning my class and bit packing. So however many, these Pokemon instances I have, and then 25 bytes less, or I guess 25 bytes more, and you can really start to see how that can add up. So it adds up pretty quickly. So it's not, necessarily hard to see why, software developers that don't necessarily care about aligning their structures, why their programs might be so bloated, because, they're taking up a lot of extra memory in some cases that they literally don't need because they just didn't align their structures properly. So part of this, I guess, was me kind of going on a rant, but also at the same time, I am definitely guilty of not properly aligning my structs. As we saw, not all of those 24 bytes that I saved was due to bit packing. Some of it was my structure was just aligned improperly. So my next plan is to kind of go back through my code base and properly align everything, make sure everything's aligned. And the way that you can actually do this, a pretty easy way to make sure that your structures and classes are properly aligned, is to do whatever your programming language's version of size of is. So in C and C++, they have I don't know if it's necessarily a function or a macro or what, but basically there's this, size of, where if you call size of on any kind of variable type or structure, what have you, it'll tell you how many bytes it takes up. And you can basically calculate the difference between manually calculating all the bytes that your structure should take up versus what size of gives back to you. So if we go back to our example here of the structs with two integers and a long, we did the math and found out that two integers are an integer is 4 bytes each, so two integers is 8 bytes. You add that to another 8-byte value, that being a long, and you get 16. So if your size of your struct is not 16, you know that your struct is not aligned properly. Now, there are potential cases where, depending on the number of variables you have and the type of variables you have, there's going to be some extra padding in there thrown in, no matter how you align the struct, just because you have various numbers of differing sizes of variable types, so it's just not necessarily possible to properly align it. Like, for example, my Pokemon struct, the optimal version of it would be 75 bytes, but because of the various different types of data types that I'm using, the best I could get was 76, no matter how I kind of try to align things, just because there were odd numbers of different, variable type values, so I wasn't able to get it down to the optimal value. But you should get as close to that optimal value as possible, just out of good practice. And one thing that we've talked about on the podcast before is that you should be striving to write optimized code and efficient code. And I guess, as I mentioned, I know might not necessarily be all that necessary to do because of how powerful and how much memory computers have nowadays. But it's just good practice, right, to write a good and efficient code rather than big bloated code. So yeah. Speaking of bloated, though, if you have a lot of bloated files, you're probably going to need a beefy network in order to transfer all those big files around, which is a great way back to our trivia question for the week, because while I don't have 40 gig networking, our trivia question does. And if you'll recall, our trivia question for the week is, what is the name of the connector associated with 40 gig networking? Now, as kind of a last-second hint here, 40 is 4 times 10. Maybe that helps, maybe it doesn't. I don't know. But hopefully some of you got it right and said QSFP+, that, of course, standing for Quad Small Form Factor Pluggable Plus. So hopefully some of you got that right. If you listened to our networking episode from last year, you hopefully remembered that. But yeah, that is the trivia question for the week. So I hope you enjoyed this episode. If you did, share it around. If you have any questions about this episode or have topics or ideas for future episodes, feel free to shoot me an email at contact@darkassassinsinc.com. Obviously, if you know any software developers out there, it's probably a good one for them, really software development oriented. But that's going to do it for me in this episode of the Dark Assassins podcast. Until next time, my fellow assassins, remember, bull nothing equals true. If action not equal to null, return true. I'll see you next time on the Dark Assassins podcast.